So, good evening, everyone. Today, I will be discussing the rest of the portion of petroleum industry. In the last class, we have discussed about uh, the source of petroleum and petroleum overview of the petroleum industry we discussed about in the last class. Today, we will be more focusing onto the characteristics of petroleum products and some details on the process description, unit operations, physical chemical unit operations, and the refinery processes. So, we can start today's class with a brief introduction to the petroleum refinery. So, the petroleum or the crude oil, it is a mixture of gas, liquid, as well as solid hydrocarbon compounds. Petroleum is essentially it is a mixture of hydrocarbons. We already discussed in the last class what are the composition of petroleum, and even the non-hydrocarbon elements like sulfur, oxygen, nitrogen. These are also present in the petroleum and making it more complex hydrocarbon mixture. The hydrocarbon present in the crude petroleum are classified into three general types, that is paraffin, naphthenes, and aromatic. Whenever we talked last class about olefins, but olefins are not actually present in the virgin crude oil. It is not naturally present in the crude oil, but the olefins are formed during the various processing. Olefins are generally undesirable in the finished product because the double bonds in the olefins are very reactive in nature, they are not stable, and the compounds are easily oxidized and can be polymerized to form gums and varnishes and other products. So they are not stable. So this is the presence of olefins are not desirable in the crude oil. So olefins, they contain 5 carbon atoms, have very high reaction rates with other compounds in the atmosphere that forms various pollutants. And even though they have a very high research octane number, but generally they are considered undesirable because they are a source of pollutants. They causes the formation of some pollutants. Those are not required, not desired as well. The combination of refining processes and operation employed, those are very complex process. Okay. Now this all the refinery processes, they vary from one refinery to another refinery, and it also depends on uh, the characteristics of the crude oil imported or crude oil being fed to the process equipments of the refinery. So based on that, the refinery operations, it varies. Modern refinery is highly complex as well as energy intensive and capital intensive. Role of the catalytic processes, secondary processing, and the hydroprocessing are increasing in the modern refinery. How, what are this hydroprocessing and catalytic processing? We will be discussing in the subsequent slides. Now, the factors which decide the complexity of a refinery, that includes nature and the source of the crude oil, that already I have told, that what is the nature or the characteristics of the crude oil you are feeding to the refinery. Based upon that, the process, all the process involved processes, it varies. Demand pattern in the markets. So, what is the demand? What are the products out of the petroleum refinery plant? Based on the demand, the processing involved will be used accordingly. Product quality and the current or near future it will be used, and based upon that product quality, the process it involved is also varies. Production of the feedstock for the downstream various operations, and also the interfuel substitution. These are some factors which defines the complex nature of the refinery operation. Discussing thoroughly the characterization of the crude oil. See, the characterization, once you have the crude oil, once you feed the crude oil, or you production of the crude oil occurs, then we need to go through the various characteristics or the various properties of that crude oil, because based upon the geological formations differences, and the crude oil properties varies a lot, and there are some characteristics indexes by which the crude oil is being defined, like this much of sulfur content, this crude has this much of sulfur content, or octane number, and other things. We will be discussing one by one in this as of this moment. So at first we were discussing about bulk properties. Bulk properties of the crude oil. First bulk property is the specific gravity. Now, specific gravity, it is the ratio between the density of the crude oil and the density of the water. That is the ratio. And the density of the crude oil and the water, that should be measured at a 15.6 degrees Celsius. Now, the specific gravity is always expressed in API unit. API is the American Petroleum Institute gravity method. This is the specific gravity. This we expressed in terms of API. Now, the equation for calculating EPI is 141 by specific gravity of that crude oil that you are wishing to get the API, measuring the API, minus 131.5. Now, this specific gravity, it should be at a, it measured should be at a 15.6 degrees Celsius. Okay. Now, it should be noted that the API gravity decreases with the increase in the specific gravity. So, this is the relation between API gravity and the specific gravity. So, the specific API gravity decreases when there is increase in the specific gravity. Now, the specific gravity of the crude oil may vary from less than 10 degree API to over 50 degree API, in the range of 10 to 50 API, but most crude oil falls in the range of 20 to 45 API range. Now you can see this graph. So this graph is taken from engineeringtoolbox.com. In this website you will get lot of information about various data of engineering related. This is very useful website. You can refer for various data that you need. This website is also useful for research purpose, because we get lot of data, raw data from that website. Okay, so in this graph we can see that API versus a specific gravity plot, and we can also see that these are marked for various fractions of the crude oil. When we do the distillation of that crude oil, we get these fractions, right? Like LNG, condensate, light oil, medium oil, heavy oil, and as well as at the bottom we will get bitumen or extra heavy oil. So we can see that a specific gravity is increased, like specific gravity is higher in case of the specific gravity, or you can say density, whatever you are saying. So specific gravity, it is a ratio, right? But the main thing, it is the density with respect to water density. It is measured like that. So whatever it is, the specific gravity of the bitumen, this is higher, right? It is collected at the bottom of the distillation unit. So it is higher specific gravity, and for this you can see that the API value is lowest. Whereas you move upwards of the distillation column, you will get CNG or LNG, the gaseous fraction, at the top of the distillation column. So that has the higher uh, API value, because there is very less specific gravity. These are very lighter. That's what it is in the gaseous fraction, right? So this is the relation that the specific gravity, when it is increased, so it means that the API value should decrease. So this is the correlation we can say based upon this graph. The next property is viscosity. It is also considered to be the bulk properties of the crude oil. So the viscosity, we all know, we have idea what is viscosity. It is the ability of the fluid to resist the shearing forces, mainly during the flow, which is caused due to the frictional forces between liquid layers. We all know viscosity, this definition, and in details in the fluid mechanics course, right? Uh, Viscosity measurement is expressed in terms of kinematic viscosity. It is measured in centistokes, or it also can be expressed in Sevolt seconds. In order to classify petroleum, heavy oil, bitumen, the use of a single parameter such as viscosity is not enough, because this petroleum, heavy oil, bitumen, these are very complex composition, right? So only the parameter viscosity is not enough to define or classify all those things. It is not sufficient. So we can see that viscosity, specific gravity, and API gravity we take, and this is the scale. You can see that with the increase in the specific gravity, as we already discussed, the API gravity decreases, right? So when the viscosity is less than 100, so it is called medium distillate. 100 to 10,000, it is heavy distillate, and more than 10,000, it is extra heavy distillate. This is the bitumen or tar sand bitumen. This is the classification we are getting. So to classify the petroleum, we need viscosity, specific gravity, API gravity, to make this scale possible to understand that how the viscosity is related to specific gravity and API gravity. You can see these numbers, right? Specific gravity, it increases when it is getting more heavier fractions. At that point, the API gravity will decrease and the viscosity will increase. It will be more viscous. It will be more viscous and more, so that it will there will be resist in the flow. Okay. So the next bulk property is the sulfur content. As I already told once, that the crude oil we are getting to the refinery, it is a very concern issue. What is the sulfur content of the crude oil? Because the sulfur content, based upon that, there will be another unit process should be employed to reduce the sulfur content of the crude oil based upon our requirement or the product quality. Also, there are such cases when we import crude oil, the sulfur content, they ask that what is the sulfur content of your crude oil that you are supplying. Okay, based upon that, the deal and other financial, economical, everything decided. Okay, so moving forward, The sulfur content is expressed as the weight percentage of the sulfur in the crude oil present. Crude oils less than 1% sulfur is known as sweet crude, whereas if it is sulfur content more than 1%, then it is called sour crudes. Always we prefer low sulfur crudes because this will require lot of chemical operations process involved. So ultimately the low sulfur crudes, these are highly demanding and high in price and better in quality. Sulfur containing compounds are mainly mercaptans, sulfides and polycyclic acids. Next bulk properties are dew point and bubble point. So, dew point we know this is the temperature at which the hydrocarbon in the gas phase will start to condense out of the gaseous phase, right? It will start to condensate. Whereas the bubble point is the temperature at which the liquid hydrocarbon, which is at liquid phase, they begins to boil and they forms the vapor bubbles. We know that the pure for any pure hydrocarbon, there is no impurities or there is no other mixture of the hydrocarbon. When it is considered to be a pure hydrocarbon, then the bubble point and the dew point are same. These temperatures are same. But when we are taking the mixture of hydrocarbons, the bubble point and dew point will be two different temperatures. Now let us quickly discuss how the bubble point and the dew point and how the temperature and pressure playing a role to create this phase diagram when we are going for distillation and those things. There will be separation of the liquid and gas phase. So this phase diagram is very important to understand that at what pressure and temperature condition it may reach its critical point, or it will be in the gas phase completely, or it will be in the liquid phase completely. So let us discuss one by one. So this is the phase diagram. Okay. Now uh, these are the tie lines you can see. So this is the bubble point line, while in this region this is the 100% liquid. So from this liquid, when it reaches to bubble point curve, then the first gas bubble will form. This is, and when it comes to this line, then there will be 90% liquid, 10% gas. So that's where it will go up to this portion when there will be zero liquid. And at that point, when it reaches to this zone, the first liquid drop of condensate will form. So this is the dew point line, and this one is the bubble point line. And below there will be two phase region. Now you can see this red point, that is the critical point. So the critical point conditions, let me write for better understanding. So the critical point where the this is the temperature of the condition at which liquid and gas are identical. This is the mm, this is the Crick that is concerning to the pressure. This is the highest pressure on the saturation envelope. Highest pressure. So you can also see this is crescendo term. So it refers temperature on the saturation envelope. The two-phase region I already discussed. This is the liquid and gas, both will be present. And see, this is the shaded region, that is the retrograde region. So at this region, what happens? Liquid condensate forms by lowering pressure or increasing temperature. So this is the brief phase diagram that always an engineer should take care of it, that how this phase diagram is changing in the processes where there is liquid gas separation. Okay. So the next bulk property we will be discussing, that is the pour point. So the pour point is the lowest temperature at which the oil will just flow under standard test conditions. The pour point of the oil is the indication of the temperature at which flow ceases. This pour point, it is very important consideration because for efficient production, additional energy must be supplied to the reservoir by a thermal process to increase the reservoir temperature beyond the pour point so that there will be smooth flow of the oil. If the pour point is very high, then there will be uh, that will be good for your crude oil, because um, So based upon the pour point, there will be additional energy requirement. So it depends. It also facilitates that how the crude oil flow will be happening from reservoir production. Next is the flash point. Flash point is the lowest temperature at which there is sufficient vapor is forming above the liquid level to form an explosive mixture with air, which can cause ignition if any spark is present. A higher flash point might be necessary for certain uses to prevent the premature ignition. Next is fire point or a fire point and freeze point. So fire point is the temperature that is well above the flash point. It is the temperature well above the flash point where the products can catch fire very easily. Whereas the freeze point is the temperature at which the hydrocarbon becomes solidified at atmospheric pressure. You need to remember that the freeze point is different from the pour point, as when we are discussing about pour point, it makes sure that the oil is very viscous. It becomes very viscous. It very hard to flow. Okay, but that is still in the liquid state. But when you are considering the freeze point, that becomes completely solid state. So these are basic differences. So next bulk properties is smoke point. The smoke point is the maximum height of the smokeless flame from burning a fuel, which is measured in meters. What is the length of the smokeless flame in meters? That is called the smoke point. A high smoke point indicates that the oil is less prone to cooking, which can reduce the efficiency of the cracking process and which can lead to equipment fouling. So, a high smoke point is favorable. Oils with lower smoke points may produce more aromatic compounds, which can affect the quality of the refined products. Also, lower smoke point indicates that the fuel is more likely to produce carbon soot and more prone to oxidation and degradation processes. Fuel having high smoke point is always recommended. The next bulk property is the cloud point. Cloud point is the temperature at which the waxes, very higher molecular weight compound waxes start to crystallize, and they become separated from the solution when the temperature is very low or when cooling. The wax deposition causes flow assurance and refinery operation various problems, and wax related problems can lead to increased in operational cost due to pipeline blockage and maintenance requirement and product quality issues. Next bulk property is the annealing point. Annealing point represents minimum temperature for complete miscibility of equal volumes of the anilines and crude oil. It indicates the minimum temperature for complete miscibility of equal volumes of aniline and crude oil. It is very important property for the diesel fuel. A low aniline point indicates the presence of the larger amount of the aromatics. Aromatics are valuable components in many petroleum products, but excessive presence of the aromatic compound can lead to problems such as gum formation and poor quality of the fuel. Next property, bulk property, is the Conradson carbon residue (CCR). It is the measure of the coke forming tendency of the oil. It is determined by destructive distillation of the oil in an absence of the air in a closed equipment. High Conradson carbon residue, that is the CCR value, indicate more probability of coke formation, which can lead to reduced the equipment efficiency. It can also increase the maintenance cost and product quality issues. So the higher CCR values may indicate a greater tendency to produce carbon soot and may contribute to more air pollution, which is not favorable. Now, one of the very important factor, that is the heating value. So the heating value, it is measured heat released from burning of 1 unit mass of oil. Knowing the heating value can help in better combustion and optimizing the refining processes to maximize the yield of the valuable products while minimizing the energy consumption. So to do this optimization, we need to characterize the heating value of the crude oil. So we have discussed lot of bulk properties of the crude oil. Now we will discuss the fractional properties. There are few fractional properties but very important for the crude oil characterization. First one is octane number. So the octane number, it is a critical measure of the resistance ability of the knocking or premature ignite properties of the fuel. Basically, octane number is very um, indicative for the gasoline fuel. So it is the how much it resistance ability of the premature ignite properties. So it is a measure of the fuel's ability to resist denotation or the premature ignition in an internal combustion engine or IC engine. A high octane number indicates that a higher self-ignition temperature. It means that the fuel will understand a high compression ratio before self-igniting. It can withstand a higher compression ratio before self-igniting. Octane number is determined by measuring the knocking value of the fuel compared to the mixture of N-heptane and isooctane. Now, N-heptane is CH3, CH2 5. This is N-heptane. This has octane number 0. Whereas isooctane is the structure is like this: CH3, 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 CH2, CH, CH3, CH3. So this is the isooctane whose octane number is 100. So sorry for this. So the octane number, it lies between this 0 to 100, this range. Octane rating is done considering the octane number of the isooctane because it has the highest value 100. A octane number 90, what does it mean? An octane number 90 indicates that the fuel performs similarly to the blend of 90% isooctane and 10% N-heptane. So the pre-ignition can lead to engine knocking, a rattle noise that can damage the engine. Okay, so higher octane fuels can improve the engine performance and especially in the high compression engines. The octane number can be improved by using various additives to the gasoline such as tetraethyl lead till it is widely used, as well as toluene, lead chlorides and methyl tertiary. So this octane number improved by using this additive, um, and by the use of this additive the octane number is improved of the fuel, which can be higher than 100 also. So you can see some octane number, it increases with increase in the compactness, double bonds and the cyclic structure of the compound. So these are some examples. Just like in octane, it is negative of 10 octane number. In heptane, I already told this is 0. Similarly, for isooctane, it is 100. So when we are mixing the toluene with the isooctane and n-heptane, so in this mixture, you can see this toluene, because of the structure and other properties, the octane value itself is more than 100. So that's why to improve the octane number of the fuel, we can add benzene and toluene into the system. The next fractional property is cetane number. So it is measured by the delay of the ignition of the fuel, that is diesel fuel you are talking about. It is represented by the percentage of the hexadecane or the pure cetane in a mixture of cetane and alpha methyl naphthalene that has the same ignition characteristics as the diesel fuel under the test condition. So cetane, it has CH3, CH2, 14 numbers, and CH3, this is the cetane. So it has cetane number Cetan number it is 100. Where is methyl naphthalene, alpha methyl naphthalene, it is like very cyclic, very aromatic and cyclic structure. So for that the Cetan number will be 0. Cetan rating is done considering the ignition of the cetane, that is having Cetan number 100. The Cetan number of the diesel fuel can be improved by addition of small quantity of the certain compounds, like you can add ethyl nitrate or acetone peroxide, isoamyl nitrite. So this can improve the Cetan number. Higher Cetan number fuels will have shorter ignition delay period. The fuels with higher Cetan number has low octane number and vice versa. Now we have discussed about the characteristics of the crude oil. Now we will move forward to the refinery processes. So on a brief introduction, refinery processes having physical unit operations and chemical unit operations. So first physical unit operation, that is distillation. We use atmospheric distillation as well as vacuum distillation. So these are separation based on the relative volatilities or boiling point ranges. Then absorption, separation based on the relative volatilities. Extraction, which is separation occurring based on the relative solubility differences in the different solvents. Adsorption, separation based on the relative adherence to the solid surface, that we already know. Crystallization, separation based on the difference in the freezing points. Heat transfer, it is based on the energy conservation. Fluid flow, there may be single phase fluid flow like liquid or gas flows, or maybe there is two phase flows like just like gas solid or liquid solid catalytic operations. Now the chemical unit operations, it is very vast. Now they involve various chemical processes that we will discuss further. So the overall refinery operation process, we can say that the crude oil is transported to the refineries by pipelines more than 5 lakhs barrel per day, or if it is coming by ocean, by means of ocean, then it comes by through tankers. The basic refinery process is distillation, which separates the crude oil into fractions based on their volatility difference. After the distillation, other physical methods are employed to separate the mixture, including absorption, adsorption, solid extraction, crystallization. These are all occurring after distillation. After physical separation into such constituents as light and heavy naphtha, kerosene, light and heavy gas oils, selected petroleum fractions may be subjected to conversion processes such as thermal cracking, coking, catalytic cracking, etc. Now the cracking breaks the larger molecules into heavier gas oils, larger molecules of the heavier gas oil into smaller molecules and lighter in weight, more valuable naphtha fractions. And also one more important chemical operation, that is reforming, that changes the structure of the straight chain paraffin molecules into branched chain isoparaffins or ring structure aromatics. This process is widely used to rise the octane number of the gasoline obtained by distillation of the paraffinic crude oil. Now you can see this is the typical refinery process chart. It almost covers overview of the all products and their subsequent processing. Okay, so we will start from this end. So crude oil is fed to the pre-treatment just like desalting and other processes. Pre-treatment and desalting. So salts are being out from the crude oil, then it is fed to the atmospheric distillation column. So in there, based upon it is occurring at the atmospheric conditions, and based upon the difference in the boiling point ranges, so you will be getting lot of different fractions. So at the top of the atmospheric distillation column, you will be getting light gas recovery. So from there will be C1 to C4 gaseous fractions, mainly methane and ethane C1 and C2. Those will be synthetic gas or fuel. C3 to C4 saturates, those will be considered as LPG, and the propelling, those are further processed through isomerization, catalytic polymerization, and then those are like after polymerization, those are taken to the detergent manufacturing unit and further like downstream processes. So we will not discuss so much details those topics. So C4, that is butylene, that is it goes for the alkylation reactor and it produce butane. It is also can be considered in the synthesis gaseous mixture. So then it comes petrol. This is the low grade petrol. So it goes for the sulfur removal where the H2S or is H2S is removed, and that H2S is sent to the H2S support plant. After sulfur removal, it goes to the catalytic reforming, and from there we get various products: benzene, hydrogen, gasoline, which has high octane number gasoline we get, and this hydrogen is further fed to the ammonia manufacturing plant to produce ammonia. And this benzene, it can also be used in the detergent manufacture. Next fraction is the solvent naphtha. So this goes as a solvent naphtha itself. Kerosene, this is like kerosene diesel fuel, it is collected as. Then gas oils is further goes for the catalytic cracking. Then it produces cracked petrol. That petrol treating and blending with isooctane, then gasoline. This blending is occurring, and then we produce the motor spirit or petrol. Then the next one will be so after the production of the motor speed, then the from the cracking, you will be getting some heating oil for domestic purpose. Now at the end, at the bottom of the atmospheric distillation column, you are getting the lubricating oil stock that you are blending with de-asphalted oil. We'll be discussing later. So at the bottom we will be getting a very residue. Okay, this residue is further taken to the vacuum distillation unit where the vacuum or under like very low pressure is maintained, and there you will be getting the product which goes for thermal cracking or the viscosity breaking. You get the industrial fuel oil, and other products goes for the propane de-asphalting. De-asphalted oil is being produced, and there will be phenol extraction method, treated oil, and then de-waxing and blending of with additives to make it more uh, uh, desirable oil, and acid treatment and other things. So focusing on the products of the atmospheric distillation unit, so you can see this is the atmospheric distillation unit. At the upper part, it is butane and lighter products, then gasoline blended product, naphtha, kerosene, distillate like diesel, heating oil, heavy gas, and the residual. This residual is further taken to the vacuum distillation unit. So let me just mention one thing, that the vacuum distillation unit, it is maintained pressure at 0.72, 1.5 psia, and temperature around 380 to 420 degrees Celsius. Okay, so as an overview, there are various process developments in the um, process development in refinery. Just we already discussed that atmospheric distillation, it was the purpose was to produce kerosene. Other byproducts, we get lot of byproducts, naphtha, cracked residues. Vacuum distillation, we mainly produce lubricants, but also byproduct as asphalts, residue, thermal cracking. The purpose was to increase the gasoline yield, sweating the byproducts. You can check one from this, but I will tell mostly the purposes. Thermal reforming for improving the octane number, sweetening to remove the sulfur, we all know, hydrogenation to remove the sulfur, coking process to produce gasoline, solvent extraction to improve the lubricant viscosity index, dewaxing process to improve the pour point, catalytic polymerization to improve the octane number, catalytic cracking, higher octane gasoline production, Vis breaking, reduce the viscosity, alkylation, increase the octane number, fluid catalytic cracking, increase the gasoline yield, de-asphalting, increase the cracker feedstock. Catalytic reforming, convert the low quality feedstock. Hydrodesulfurization, it is removal of the sulfur. Inhibitor sweetening, remove of the mercaptans. Catalytic isomerization, convert to high octane products. Hydrocracking, improve the quality and reduce the sulfur content. Catalytic dewaxing, improve the pour point, and resid hydrocracking, increase the gasoline. So this gives the overview what was the purpose of having that process included in the refinery. This is like throughout the year of throughout the decades it has evolved that much, and to maximum product recovery we are having this many of chemical processes. Next we will discuss one by one the refinery conversion processes. I will discuss this section very briefly. In detailed description, it is already there in the NPTEL lectures. You can refer to those lectures. Uh, for these refinery conversion processes, I will just touch upon and mention the major highlights of this every conversion process. So, starting with pyrolysis and catalytic cracking. Pyrolysis is a thermochemical endothermic conversion at high temperature in absence of air. So pyrolysis occurs in the absence of oxygen, and endothermic because it requires lot of energy to convert the pyrolysis product. Thermal cracking. Non-catalytic pyrolysis and the catalytic cracking are possible in petroleum industry to crack longer molecules into smaller ones. Now the catalysts are used in pyrolysis to lower temperature. The purpose of using catalyst is to lower the temperature and pressure of the process to obtain a higher selectivity of the cracking with less side reactions. Reactors used are fixed bed, moving bed, and fluidized bed. Those are highly used in the cracking process. First one is the thermal pyrolysis reaction mechanism involves three steps. One is thermal cracking. It follows the free radical mechanism. That is, it produces the olefins and same small free radicals, and the reaction terminated when the free radicals species react with other solid or each other, and they at that point the reaction terminated. So then the next step is the thermal polymerization. So these olefins will get polymerized to form the larger molecules. And cooking, so there will be lot of formation of the free carbon when the hydrocarbon undergoes complete degradation, so there will be carbon deposits. That is cooking. So in the thermal pyrolysis reaction we get adequate quality of C1 and C2 fractions, which refers to lot of gas fractions is occurring in the pyrolysis and pyrolysis process, thermal pyrolysis process. When sorry, this should not be thermal pyrolysis. This is catalytic cracking. Catalytic cracking in a reaction a mechanism involves it produces no gas fraction at all. Greater aromatic portions are produced, and reaction mechanism solely depends on the choice of the catalyst. More isomerization of the small hydrocarbons, and two secondary and tertiary hydrocarbons, and less polymerization is occurring. Relatively little coke formation occurs compared to the pyrolysis process, and produce high quality petrol from any crude source, octane number in the range of 80 to 90. Other points that is very important reaction condition to be followed for pyrolysis and catalytic cracking. One is the optimum time, pressure, temperature. Those are very common. You have to take care of these parameters. And another one is the catalyst to feed ratio. Now the selection of the catalyst is very crucial factor for the catalytic cracking process. Properties of the catalyst, that is composition, what kind of, in what form this is present catalyst, their regenerative properties, their poisoning effect or the limit, and the aging process. So in general, acid treated silica, alumina, this is used as a catalyst, and also natural clay, just like bentonite or kaolin, these are also used as a catalyst for various processes. And this catalyst can be used in forms of pellets, that is 3 to 4 millimeter for the moving bed, and it can also be as a spherical, microspherical to 20 to 80 mesh size. This is used for fluidized bed. Talking to the regenerative properties, so um, these regenerative properties must be very high, that is desirable, and we can use reheating of the using CO2 or carbon monoxide for better heat control in the reactor. Poisoning effects is also important permanently, because if it is permanently poisoned, then it can be used further, right? Catalyst should be high tolerance toward any kind of poisoning, sulfur poisoning or any kind of poisoning. It should not be that sensitive to the poisoning agent. And aging also an important factor, because when there is continuous operation is going on, then there will be reduction in the surface area. Reduction in the active surface area, and that was there is a loss of reactivity of the catalyst. So this is not desired. So at that process, catalyst may be required to be replaced. So next process is the reforming process. Catalytic cracking is or reforming is to convert the hydrocarbons to aromatics or having higher octane ratings. Now the feedstock for the catalytic reforming is various naphtha grades. Those have boiling range of 60 to 200. So less than 100, that will be light naphtha, then intermediate naphtha, then more than 100 or like that, that will be um, heavy naphtha. So the virgin naphthas, those are used as a feedstock for reforming, that is crude oil distillation unit, coking naphtha from petroleum coking processes via pyrolysis, and catalytic naphtha, those are produced from catalytic cracking processes. So you can see these are the reaction involved in the reforming. First one is dehydrogenation. Dehydrogenation is the methyl cyclohexane. Hydrogen is being removed from this system and it becomes toluene. So it has very high octane rating. Cyclization, it is N-heptane and dimethyl cyclopentane. So you can see in that reaction that it becomes a cyclic compound. This is the methyl cyclohexane. Isomerization, that is um, ethyl cyclopentane, it becomes methyl cyclohexane. Isomers form. Hydrocracking, that is the N-heptane, it produces propane and butane. So this hydrocracking is not desired because it produced very low octane rating compounds. Those are not required. So dehydrogenation process is very important step. Other important some highlights that for catalytic reforming, dehydrogenation catalysts are mainly required, and that catalyst may be platinum, molybdenum oxide, chromium oxide, cobalt molybdenate, alumina and silica alumina base. So this platinum is the best options in terms of selectivity, but it lacks hydrocracking and activity and also expensive. In catalytic reforming process, whatever carbon deposit takes place on the catalyst surface, that is the aging process, can be removed by oxidation or can be removed by air flowing or air oxidation. Reforming is done under high hydrogen pressure so that many catalyst poisons, that is sulfur, nitrogen, whatever poisoning of the catalyst occur, that becomes hydrogenated, and consequently that can be removed from the surface, and we can regenerate that catalyst. Dehydrogenation process, that is very important process that we discussed in the last slide. It is feasible at low pressure and high temperature conditions. Now the catalytic reformates make excellent blending stocks since they contain no olefins, and these reformates are very chemically stable and having very high octane values. The product of the catalytic reforming. However, carbon deposit can be suppressed by high hydrogen pressure with use of the product hydrogen recycle. In general, a compromise is made between catalyst activity and the yield of the reformate of a given octane number by typically resulting conditions. Like catalyst, if you are using platinum, pressure 30 to 15 to 30 atmosphere, temperature around 470 to 525 degrees Celsius, space velocity is 1.5 kg per hour. So this compromise is made between catalyst activity and the yield of the reformate. Next process is the polymerization process. So there, what is polymerization? Combination of the two or more olefinic molecules to yield more larger molecules. Example like polymer motor spirit. Acid catalysts are used for this polymerization. Example like 65% H2SO4. For the cold press process, temperature is maintained 20 to 30 degrees Celsius, whereas for the hot process it is 93 degrees Celsius. Liquid phosphoric acid is also used. Phosphoric acid on inert carriers such as Kjelgur or silica. Copper pyrophosphate on the charcoal solid catalyst are also favored. So the reaction involved, first one is the carbonium ion formation. You can see that olefins, hydrogen catalyst that you are using acid catalyst, you are having H plus ion, and there you produce this carbonium ion. The next step is the addition reaction, that this carbonium ion, it reacts with olefins, and then again it forms this kind of structure. Regeneration, then it forms the dimers plus hydrogen plus ion regenerated, and isomerization, it forms this isomer. Okay, next one is the alkylation process. So it is very similar process to that of the polymerization, but here the olefins react especially with isoparaffins, not with other process. So and the alkylate produced is approximately twice the quantity from a given volume of the olefinic stock. It is very higher quality product that for the petroleum blending we can have, because it is composed entirely stable and saturated branched paraffins. Okay. What are the reactions involved in the alkylation process? First, similarly, carbonium ion formation that we already discussed in the polymerization reaction, carbonium ion formation. Next one is in the presence of acid catalyst we are using. So we are using here also acid catalyst. Carbonium ion formation is the first step. Then again it follows the addition reaction, which forms the carbonium ion intermediates form. And then the last one is the regeneration. The same followed, just like same as polymerization reaction. Catalyst here that is used H2SO4, HF hydrogen fluoride is also used. So the next refinery conversion process is the isomerization process. So here what happens that catalytic isomerization is occurring of the normal paraffins. It forms isomers, various isomers, right? So see, this normal paraffin like this structure is converted to isomers, and this is exothermic reaction. Now the catalytic isomerization is occurring. So the catalyst use the aluminium trichloride, acyl promoted one. Here the reaction temperature and pressure, you need to take care that temperature around 100 to 150 degrees Celsius, pressure is around 17 to 27 atmosphere. So it is nothing but converting uh, the chained flat chained paraffins to um, isomers of that paraffin. So it is also important. The next one, the next process is dehydrodealkylation, sorry, hydrodealkylation process. So this process uh, reforming that produces equal yields of benzene, toluene, and xylene, that is BTX we called. So here we apply the hydrogenation and dealkylation process. So that's why it is called this one. So this is nothing but if we, this is the hydrogenation process combined with dealkylation process. So this part, it is like uh, for benzene we do operations on that hydrogenation and then dealkylation. So there are this much of refinery conversion processes at present. We discussed about almost 6 processes. So at the end of the petroleum product that we are getting as a end product, so we need to take care of various purification processes, just like removal of the suppose purification of end petroleum products. So here that is the removal of the sulfur and the mercaptans. First one is removal of sulfur like various mercaptans and H2S and other things, sulfur compounds. So these are treated with strong H2SO4 acid or mild oxidants. Catalytic oxidations are also occurring and hydrogenation process is also obtained to remove this sulfur compounds. Next is the removal of comes color order. So this is performed again using very concentrated sulfuric acid and clay adsorption, and improvement of the stability. So use of the mild hydrogenation process if any unsaturation is occurring. Otherwise, the other treatment listed before we discussed that also can be improved, can be used to improve the stability. So this is like more details we will discuss in the petrochemical industry one by one. There will be again this discussion of these processes. Yeah, so this class is this content is up to this portion. So if there are any question, then you can ask in the question answer session, like in the question answer um, section of the NPTEL. If you have any specific doubts regarding this lecture. Otherwise, we will shift to the petrochemical industry in the next class onwards. I have tried to focus on the other parts of the petroleum refinery as much as possible in detail other than the NPTEL lecture. Some of the notes are very similar of the NPTEL lecture because those are the like crucial thing that I wanted to discuss, that is important also as a part of the petroleum industry. So that's it for today's class. I hope you people join for NPTEL lecture, this live session. This will be very helpful for one-to-one interaction